Okay, good morning, everyone, and welcome to our webinar on leveraging complete interactive time series modeling workflows. Yeah. My name is Wembai Maprisa, and I'll be taking you through this presentation. I have an honors degree in computational and applied mathematics from WIS, and I'm a consultant at Optimum Solutions. My interests are in finance as well as economics. To start with, we will look at our agenda. So first, we'll look at defining a time series, and we'll go through a demo with some examples in MATLAB. We'll look at a case study, and we'll then conclude our webinar. So first, what is the time series? So this is sequential numeric data points in successive order that depend on time. So this is data recorded hourly, daily, or monthly. These data points then provide insight into the change of prices of financial instruments over time. So this could be our stock data or commodities, right? We can then use this information to forecast and predict. Creating these models, though, can be time-consuming and difficult. So we'll look at how MATLAB can help us with this flow. So just to look at our workflow when working with time series data, the first thing we do is we define our problem. We then go into some preliminary analysis where we want to find trends and cycles in our data. And then we go into model creation. We choose the best model and we use it to then focus and predict our data, which is then the evaluation part. We will then see how MATLAB can make the preliminary analysis, the model creation, as well as the evaluation easier. So also important to note that metrics functions are quality tested and controlled, so they are all reliable. So just to look at our examples, we'll look at our first example of univariate modeling, which is for the S&P 500 index data. We'll look at predicting the returns as well as the general behavior. We'll then go and look at a second example, multivariate modeling for the US GDP. So we then illustrate how we can use the univariate modeling workflow and replicate it in the multivariate case. We'll go through data processing, interactive model creation, as well as test and returns forecasting. We will now go into MATLAB. So this is our MATLAB, and for the sake of this demo, I will just use the live editor. So just to reiterate, for our first example, we will look at how we can focus the S&P 500 index data in MATLAB. So to do this, we'll go through importing data, we'll go through some data preparation, fitting a model, validating that model, as well as then going to update that model. Right, so when we're working with time series data, we observe dependencies on lagged returns and innovations. To capture this behavior, we use the autoregressive integrated moving average models, the ARIMA models. Right? So what we're trying to do is focus time series data into the future. We also observe that financial time series data contains volatility. This is the clustering behavior. So to capture this behavior, it is best to use Gauch models, the generalized autoregressive conditional heteroscedasticity models. So first, we'll look at importing data. So what you observe here is that we have a table of contents that allows us to skip to each section that we want to look at. Right, so we'll look at importing data. So in order to import our data, here we have the data from Ferret function. So what this function does is using the data field toolbox, we can then retrieve S&P 500 index data from the Federal Reserve Economic Data Service. So what this toolbox allows us to do is it allows us to retrieve data from providers like Bloomberg, FactSet, and Thomson Reuters. We need to specify our from date and our to date, as well as the data that we are looking for. It then downloads the data for us. So now we can look at visualizing that data. What we have here is a plot of the S&P 500 index data prices. So we'll then just zoom in on this data just to see what's going on with our data. Right? If we zoom in to this data, you see that as we go in, we have missing points in our data. So this is data that wasn't recorded. This is when the market is closed for weekends as well as public holidays. So we'll see at how we can then use this in our data preparation. Right, you also observe that we have this gray shading for our recession. So we have a recession plot that allows us to do that, which is quite helpful. Right. We also have a load function that we can use to load our MET files. So this allows us to load our data and then we can use it in any way we wish to. So we'll look at our data preparation. So we need to transform data to stationary data sets, right? This is because our data is best interpreted when it is not a function of time. So we need to detrend our data. So in this example, I will use the tick to rate function, which essentially uses datetime to convert price series to return series given periodic observations. So we will now have our returns data using that. So because we observed gaps in our data, we can then look at removing those gaps so that we can go into modeling. What we use here is the isNone function. What the isNone function does is it then looks for the points where we have missing data and then we can remove them. So this is what has been done here. What you can also do is use a clean missing data task. So what this task does is it allows you to specify the data that you want. It allows you to specify the variables. It allows you to specify your x-axis, and then it removes the missing data for you. You'll find here that we have number of removed missing entries being 0. That's because we've already used the isNone function to clean our missing entries. If we open that, right. If we zoom in on that, you will then find that we no longer have missing chunks, which is great. You also find that as I zoom into this data, our x-axis moves, which is very helpful. So you find that our task is quite useful. What we also find is that this task has data. So this data has code. So this code is reusable in any way that you want to. So you can then just use the code instead of the task itself. So this is then just a plot of our returns data. If you zoom into that data, you will find that we no longer have any missing parts, which is great. So after differencing our time series, you might find that we still have that our data is not stationary. So we'll look at doing some tests to make sure that our data is indeed stationary so that we can do our modeling. Right. So the first thing we do here is split our data into a train and test set. So what the train set does is then it helps estimate the model parameters, and then the test set can then be used when making predictions. Right. So we'll use the most recent 2 years of our MET file as our test set, and the rest will be used as a training set. We'll then go into our app. So there are 2 ways of going into the econometric modeler app. The first way is simply typing econometric modeler into your command window. The second way is going to your toolstrip, going to the app section, and then you will find here, if you go to this drop down, you will get all your apps that you have in your MATLAB. So you will find that I have my econometric modeler here, but given that if it's not part of your favorites, if you scroll down, if you go to computational finance, you'll find your app. So just waiting for that app to open. Okay, so here's our app. So the first thing to then do in our app is import our data. So there are 2 ways to import this data. You can import from your workspace, or you can import from a MET file. So because I've done the separating of my data in my live editor, and I've also saved the variable in my workspace, I will take that from my workspace. I then get this prompt that allows me to choose the data set that I want. So I can then import that data. So immediately it plots the data that you want to look at. So this is our train set. And then we can look at doing some tests on this data and just making sure that our data is stationary, right? So the first test I will look at is a Phillips parent test. So you go to new test and you'll find our Phillips parent test. So this is a test for a unit root. You'll find that our null hypothesis says our trained data set contains a unit root. We will have some parameters here that we can change, which I'll leave to default, and then I will run that test. So we get it true. So our true here means that we should reject our null hypothesis. So our trained data set does not contain a unit root. Okay, I will go back to econometric modeler, and then we'll look at doing another test, a KPSS test. This is a test for stationarity. So our null hypothesis says our returns data is trans-stationary. You have some parameters here, but I will leave them to default and run the test. So we get a false. So we should not reject the null hypothesis. So our data is indeed trans-stationary. So to characterize the time series, we can then do some autocorrelation function plots. So if we go to plots, you'll find that we have the autocorrelation function plot. We also have the partial autocorrelation function plot. I would then drag that so we can visualize them together. You'll find that there's no obvious pattern to work with for both plots. So there's no evidence that the vertical lines geometrically fall to zero. We just have a significance at lag 1, right? So we know that we then can choose the AR1 model or an MA1 model to fit our data. So this then suggests that our data could be governed by white noise. So I would then go into doing more tests before modeling, right? If we go back to econometric modeler, I will do a Young box Q-text, which is a test for autocorrelation. So the null hypothesis says the first M autocorrelations of our returns data are jointly zero. I will run the test and then we get it true. So we should then not reject our null hypothesis. So our first M autocorrelations are not jointly zero, right? I will then do another test. I will look at doing an Engels arch test, which is a test for heteroscedasticity. We will run the test. We get it true. So we should then not reject the null hypothesis. So we should then reject our null hypothesis. So our trained data exhibit arch effects indeed, right? So after doing that, we can then estimate our model. If we go back to econometric modeler, we have some models here. We can look at then estimating our ARIMA model. Right, so you get this these options coming up. We want an ARIMA 101 model since our significance was at lag 1. If we go to 1 and then 1, we want a degree of integration to be 0, as we've already done the differencing. We'll use the Gaussian innovation distribution. And then if you go to details, you'll find some details on the model, and then we estimate this. So you have your parameters here, your goodness of fit, your model fit, as well as your residual plot here. You'll find that we have a p-value of 0.1237, right? So what you can then do is do a residuals QQ plot. Yeah, and then we get a plot of our residuals. So what you can then do is look at exporting your model, right? So MATLAB generates codes that you can reuse in any way that you want to. You can then generate a function or generate a live function. So you can then use this code to automate your code if you wish to. So this is our function. If we go back to our econometric modeler app, We also find that we can generate a report in MATLAB. So it documents everything that we've done in the app so that we can share the report should we wish to. So we can then choose that we want all the work that we've done on the time series returned, as well as the model itself. You have different formats to pick from here. I will keep PDF. Then, okay. We save that as test and ARIMA. So after pressing save, what MATLAB does is it runs through everything you've done in the app and starts generating the PDF for you. So we will give that a minute. Okay. So here's our PDF report. So this is our table of contents, and this is basically everything we've done in the app. So we had that plot come up, we did the plots, our KPSS test, Phillips-Perron test, Engels arch test, Young-Book skew test, our model estimation towards those plots. So I will now go back to the live editor. Right? So you'll find that everything that I've done in the app can be done programmatically in the live editor, right? You will have that these are the tests that we've already done in our app. What you can do is when you get the material is just look at the detail of these, but this is basically just functions that are also in our app. So our plots, which we've all done in the app, right? Okay, so this is the ARIMA model that we've estimated in the app. Okay, so now in order to optimize our model, we'll then need to look at our AIC, BIC values, right? So we need to know how good a model is at explaining the relationship between variables. So this is why we use our AIC, BIC values, right? We're trying to find the perfect midpoint where the complexity of the data does not overpower the simplicity of the model and vice versa. So when we're looking at it in our AIC, BIC value, the smaller the value, the better, right? So we will then go through 5 flags and just get the value the minimum value of our AIC, BIC value. So this is just an example. And then we can use parallel computing for that. We find that our model is optimized at ARIMA 102. What we can do is go back to the app. We can then go to our time series, click on our time series, then go to our models, click on our ARIMA so that we can estimate a new model, right? So we want to estimate an ARIMA 102. Right. So we estimate that. Okay, so again, your parameters, your goodness of fit, your model fit, as well as your residuals plot, right? So just so we can then compare with our 101 model. Right? You will find that in our 102 model, we have a p-value that is less than our 101 model, which is great. And our AIC, BIC values are also less than that of our ARIMA 101. Right? So again, after doing this, you can then export your model, and you can also generate a function and as well as your report. Okay. So we will now look at our Gauch model, right? So it appears that we have arch effects in our data, right? And just doing a plot of our returns, we see that 2008, 2009, as well as 2020 have spikes there. And to capture this volatility, we will then use the Gauch model, right? So we would do an autocorrelation function plot as well as a partial autocorrelation function plot for our squared returns, just to look at that. So in this case, we will then just do everything in our live editor just to show that everything can be done programmatically, but you will have your gauge model in your app as well, so you can go and estimate that thing, right? So looking at this plot, we observe a decreasing geometric pattern and two significant values in our partial autocorrelation function plot. And then we can then use our gauge model. So in the first instance, we will then estimate a gauge 1-1 model. So after estimating a gauge 1-1 model, we observe that we have a p-value that is less than our ARIMA 102. We also have an AIC-BIC value that is less than our ARIMA 102, right? So just to look at that, if we scroll up, we have our ARIMA 102 here, as well, so our p-value as well as our AIC-BIC value, just for comparison. Okay. So by inferring the data and plotting it against the returns, we can then see that inferred volatility spikes with change in our returns data, right? So this means that our gauge model is good. So we can then work on combining our ARIMA and our gauge model in order to optimize the model. So this is then the combination of the two models, and we will get a p-value that is less, as well as an AIC-BIC value that is less. So our ARIMA gauge model works better than our gauge 1-1 model, which is great, right? We can then forecast the returns using the ARIMA gauge model. We will use the test set that we had created above, and then we find here that though not quite accurate, we can see that we are getting a somewhat good forecast in the general behavior is not too off. In our case, this is okay because not much work has gone into pre-processing our data as one normally would do. And this is just a simple way of creating ARIMA gauge models. So this is what we find for our forecasted returns, right? We will now come to the end of the univariate modeling and look at multivariate modeling, right? So again, for this, I will go into our app. In this case, I will import a new data set. This time I will not import from the workspace, I will import from a MET file. So what you get is this prompt that tells you that after importing a new data set, it will clear everything that you've done in the app, which is okay. I will import my data. Okay, so what we want is this timetable being imported. Right, so what it then does, it plots the different variables that we have. So you can then just look at that, and then you have all the variables that you have here. What you'll see that is you can delete, you can export, and you can also just open to visualize the data whilst in the app, which is great. So you can difference, you can detrend, and we have some models here. So again, just like the univariate model, I'll look at doing some tests. I'll start with the Bosley collinearity diagnostics. So this is a collinearity test. Okay, so this is what we have here. You will find that the econometric modeler highlights some rows in yellow. So these rows that are highlighted exhibit multicollinearity. So you will find that you can also remove as well as add time series in this table. Right? So you can remove that and you can add that back, right? Which is great. We can also then go into doing another test. We'll look at an angle Granger test, which is a test for co-integration. So again, like your univariate testing, you'll find that we also have multiple parameters here that we can change. We'll just change that to GDP. We will then run this test. Sorry. Okay, so one thing I neglected to mention is that because this takes in 12 variables at most, so you then choose the variables that you want to look at. What's your hand? We choose that, and we have our GDP here. We can then go into doing the test. Okay, so again, you have those parameters to change. I will change this to GDP and keep everything as default. I'll run this test. So we have a false, so we should not reject the null hypothesis. So there is no co-integration between the time series, right? So what we can then look at is doing some plots just to visualize the behavior of our data. If you do a correlation matrix, you would then find the relationships of your various variables, and then you decide which variables you want to keep as well as the variables that you want to discard. We'll then just look at doing autocorrelation function plots as well as the partial autocorrelation function plot for our GDP. Okay, I'll drag that. Okay, you will find that we have that geometrically decreasing pattern, and we have a significance at 1, right? Okay, so we can then look into modeling, right? We go back to econometric modeler, uh, we choose the variables that we want. So these are the 3 types of modeling that you can then do. So you can do a vector autoregressive model, a vector autoregression model with exogenous series, as well as a vector error correction model, right? I will take a vector autoregressive model. Right. So unlike our univariate modeling, this time the estimation is done using matrix, right? So I will leave our autoregressive order to be 1. And again, you have the details which will allow you to get help on the model, and then we estimate this. So again, you'll find here that you have your parameters, your goodness of fit, your model fit, as well as your residual plot. We'll change that to GDP, right? And then we can just visualize the behavior of the GDP when modeled using the other variables, right? We have the different p-values here with the changing parameters that we have. So we can do our residuals QQ plot here as well, just to look at that. Okay, so you'll find that your residuals QQ plot is done for all the variables that you've done in your estimation, you've used in your estimation. So again, you can export the model, you can generate a function if you wish to automate your model, or if you wish to use code outside of the app, and you can also generate a report. Okay, so that brings us to the end of the multivariate modeling. Right. So coming from our demo in MATLAB, what we've observed is that MATLAB is user-friendly. So you can make use of the econometrics modeler app, which is very easy to use and does not require any coding. And you also have live scripts that allow us to include live tasks, which require no coding as well. There is central data importing and processing, so everything can be done in MATLAB. And you have the key characteristics of your model provided and accessible. So the app has the functions and you don't need to create any. You have automated reporting features, so you can then generate your functions or your documenting for reports, which is great. right? We will then look at a case study. So this is macroeconomic modeling and inflation rate forecasting at the Reserve Bank of New Zealand, right? So the primary function of the Reserve Bank is to formulate and implement monetary policy to maintain price stability. So the challenge was to support the monetary policy with a theoretically well-founded model. The solution was to use MATLAB to analyze and forecast macroeconomic variables. And we find that making use of MATLAB, one, can facilitate forecasting as well as give a detailed economic story that helped the Reserve Bank of New Zealand explain its projections to the public and other stakeholders. So they took advantage of MATLAB and third-party toolboxes, both specifically for macroeconomic forecasting. And as a result, MATLAB completed their entire workflow. They were able to share code with other central banks because MATLAB is broadly used, and results could be easily shared across the central bank for further analysis of the model and improvements. Right. So just to look at some key takeaways, as we have seen in the demo, we can rapidly build univariate and multivariate econometric models using MATLAB. There is an increase in model workflow automation. There is code generation from apps and tasks, and you can customize models built interactively with low code or no code customization. So you can make use of our apps and our tasks which allow for no code and our functions that allow you to not code it or as well, right? And then there's automatic generation of production ready model code. So models can then be exported from the apps, which you can then use. So some next steps, you can speak to us about licensing and training, as well as any technical problems you may experience in MATLAB, and general queries around what we do. So you will find us on the various platforms listed there, so you can connect with us on any of those. And then we'll move on to questions. You are welcome to unmute yourself and speak, or just post your questions into the chat. All right, I see there is some typing going on, so I will give us some time. Okay, no questions. Cool. Right? If there aren't any questions, we can then move on to the frequently asked questions, right? In which toolbox could I find these functions in econometrics modeler app? You'll find those in our econometrics toolbox. And I have heard about timetables in MATLAB. Do they offer any advantages? So when you're doing multivariate modeling, right, sometimes your time series may not be synchronized. So if your data is disorganized, you can then use the time series to synchronize that data and do the multivariate modeling in the app, which is quite useful. And then what if I have an existing models in another language, right? MATLAB is interoperable with other languages. So you can then use MATLAB for whatever you want to do here with the other languages as well. And how good are time series models on evaluating the performance of an asset? So time series help us extract trends, right? If you want to invest, you can look at the seasonal trends, and using the time series, you can then predict the volatility clustering as well. So time series are quite useful when looking at assets. And then I've had MATLAB is only good for prototyping, but that means I have to recode in another language. Can MATLAB code be deployed into a production environment? So we have a wide range of options for deploying and sharing applications developed in MATLAB. So we have a compiler that you can access deployed packages through applications written in Java, .NET, Python, C or C++, right? And can I deploy MATLAB into an environment with other languages? And the answer is yes. MATLAB supports multiple languages and open integration with enterprise systems via APIs. And then the last one, can MATLAB perform DSGE modeling? And the answer is yes. There are several free available toolboxes to perform DSGE modeling, right? So if there are no questions, we'll then come to the end of our webinar. Thank you so much for attending. Have a great day.